Hello, everyone. I'd like to welcome you to PyData Global 2024. Built, built brilliant software developers Bill Engels and Chris Fonnesbeck from PyMCA Labs. PyMC Labs will be giving their tutorial making Gaussian processes useful. And I'd like to hand it off to you two, and thank you so much and everyone else for attending.
Thanks very much. Yeah, we
Thank you.
didn't tell him at all to say that we were brilliant. He just came up with that on his own. Thank you, Stephen. Yeah, welcome everyone. Thanks for tuning in. Bill and I appreciate it. This is going to be kind of a tag team effort. I'm going to do the boring background introduction to Bayes and Gaussian processes, and then Bill's going to do wild and wonderful things with Gaussian processes that will hopefully make you want to use them in your own work. So, this is a little bit different than other GP talks that I've done. We're going to make no assumptions about what people know ahead of time. So I'm going to start from the beginning and explain probabilistic programming and Bayesian inference and a little bit of hierarchical models, and then jump into a little bit of Gaussian processes. So it's not going to be very deep. It's just an introduction to hopefully allow you to use them effectively within the context of PyMC. So what we're doing here broadly is Bayesian inference, which is from a computational standpoint, sometimes referred to as probabilistic programming. And really what we mean here is that we're writing software programs that are partially random, partially dependent on random numbers. So the outputs are not deterministic. And really you can use, any language with a random number generator to do this. But if you want to do yourself a favor, you want to pick a probabilistic programming language that has some built-in functionality that allows you to work with these random number generators and probability distributions more easily. And what you can think of them as essentially are sort of primitives related to random variables. So we have random variable primitives. So in addition to integers and floats and strings, we now have variables that are, let's say, a normal distribution. And we can draw values from that. So it's a distribution over particular values that get drawn from NumPy or PyMC or wherever. More broadly, though, you can have distributions over, let's say, functions. So a Gaussian process, as we'll see, is a distribution over functions. So when I make a draw from a Gaussian process, I get an entire function. And I can make predictions with that function. One of the nice things it allows you to do from the standpoint of Bayesian inference is that it allows you to condition between variables. So in the last piece here, let's say I have some probability, P, and I'll assign a probability distribution to that. We may not know what it is, so I assign it a beta distribution. And then we make another distribution conditioned on whatever value P happens to take. So we draw a value Z from a Bernoulli distribution that has probability P. All right, so this conditioning, Z given P, is something that we can do. And this allows us to specify really complicated models, sort of component-wise at a very high level. And what this ultimately does is that it makes it very easy for us to specify and then fit Bayesian models. And Bayesian models traditionally have been very difficult to work with, which is why, if you went to high school a long time ago, like I did, you didn't actually learn them, or even in college, you didn't actually learn very much Bayes because it was hard to do computationally. Probabilistic programming languages allow us to do that. Bayesian inference is not just a specific type of statistical model. It's actually an entire different paradigm than classical statistics. And so it's useful to understand a few of the kind of the theoretical underpinnings of this statistical paradigm. Okay, and so what we're trying to do in Bayesian inference is we're trying to make probability statements. It's all about working with probability statements. So theta is going to be a bunch of parameters in our model that we don't know, that we're interested in, and y is going to be our data. So we always have these, right? We have unknown variables that we're trying to learn. We have data that we've collected that we hope has some information. And then we have a model that relates the data to the parameters. So this PR paren is our probability, it's our probability model, and it involves both theta and y. And so we can consider this joint probability distribution, and using the rules of conditional probability, we can break that joint probability into a couple of components. One is, what's the probability of observing our data for any particular value of an unknown parameter? And then, what's the probability of our unknown parameters? These are kind of two pieces that make it a lot more tractable than considering the joint distribution. And this is just the rule of conditional probability. This is just a law of statistics, essentially. That's one way of breaking it down. The other way of breaking it down is this way. Think about the probability of our parameters, our unknowns, given our data. This is actually what we're interested in, right? We want to know, what do we know about our unknown parameters, our model, given that we've collected this data that we hope is useful, right? So this is just a different expression of conditional probability. In fact, if we drop this definition into the numerator of this expression, we get something known as Bayes' formula. This is Bayes' formula. This is the estimator for doing Bayesian inference. And it involves a prior probability, what we know about our model, about the parameters of our model before we collect data, some model for our data, the likelihood, we call it the likelihood or the sampling distribution, and then the posterior distribution, what we know about our model after we've observed the data. So we can think about this as a learning tool, learning about unknowns, about models from data. And that's the goal of machine learning in general. The thing that doesn't get as much attention, but is just as important from a operational standpoint, is the denominator here, the normalizing constant. This turns out to be a really big integral. It's the integral of the numerator over all of the unknowns. And if you've got a lot of parameters in your model, it's a multidimensional integration, which is really, really difficult and is actually impossible to do analytically, and it requires numerical methods. So what we're mostly doing in probabilistic programming is kind of ignoring that fact and letting sophisticated probabilistic programming software take care of that numerical integration piece and working with the things that we do have, which is a model for our data and models for what we know about our parameters. And we'll use that to infer the posterior. So the goal is to get the posterior distribution. So what we have to do as probabilistic programmers is specify a likelihood and priors for the things that we don't know. And priors can take many forms, right? So for example, we might have a regression parameter like a slope, and we could assign that a normal prior with mean 0 and standard deviation 1. And what we're saying here is that, we don't know what it is. It could be positive, it could be negative, but it's probably within 2 or 3 units of the mean. This is also a normal distribution. Looks very flat, but it's got a standard deviation of 100, so a variance of 10,000. And so over the range -10 to 10, it's essentially flat. And this is saying we actually know almost nothing about theta. It implies kind of ignorance. Or we're going to talk about in a bit some baseball, something like a home run rate. Professional baseball players hit home runs a fair bit, but not a ton. And so a beta distribution describes probabilities between 0 and 1, and you can parameterize a beta distribution such that most of the probability is in a range that we see in real Major League Baseball. That's kind of the idea. The likelihood function is similar. You specify how data are distributed. Often data are normally distributed. People's height, people's weight. A thing called the central limit theorem guarantees that sums of random variables or functions of random variables tend to be normally distributed no matter what they are. So often data are normally distributed. What we're going to talk about here in in the baseball context is things like hits and home runs, where a batter will go up to the plate, several hundred times in a year, and over that course of that time, they'll get a certain number of hits or home runs. And so that implies a binomial distribution. It describes the number of successes, i.e. hits or home runs, over a set of trials, each at bat being a trial. Okay, so this is a discrete likelihood. The normal distribution is continuous. People's height and weight are continuous. A binomial distribution's discrete. So we're going to focus here on baseball because we like it, and it's cool. And so, I'm going to talk a little bit about home run hitters. So this is Giancarlo Stanton. He hits a lot of home runs, and we want to try to estimate. We observe players hitting home runs or not, and we want to estimate maybe their kind of underlying talent. And if they have a lot of at-bats, they get a lot of trials, we are better able to estimate that. The fewer number that they have, the harder it is to do. And we've got to apply some statistical tricks to do that. So our data looks like this. We got players of different ages. So there are covariates here that could affect performance. And there's many more columns to the data set than this, but this is what I'm going to be using for now. So let's come up with a model for estimating the underlying home run probability for different players in Major League Baseball. And I've actually already shown you the components that I'm going to use. This is one of the easiest statistical models you can build. There's only one unknown here. Actually, there's as many unknowns as there are players, but for any given player, there's one unknown, which is the unknown probability that they will hit a home run. And we're going to assign a beta distribution to that. And then the home run rate will be modeled with, the home runs themselves will be modeled with a binomial. And so for a given probability, you expect a certain number of home runs, and that's what the binomial distribution describes. So let's move over. Let's actually do some Python. We're in PyData. So this is what a PyMC model does. So PyMC is just one of several libraries for building Bayesian models in Python. And it's a very high-level interface. So much so that for every line of math that you can write down on a whiteboard, you typically have one corresponding line of PyMC code. And so what we do is we specify a model here, PyMC model object, and we use a context manager for that. So we open it up with a with statement, kind of like we were working with like a network connection or opening and closing a file, except this time we're opening a model, creating a model, and then anytime we declare a variable, a random variable inside of this model context, it adds it to the model. So it's the way that we build a model in PyMC. We just declare variables, and then those variables get added to the model. And so the first line here is our beta distribution, and parameters alpha equals 1, beta equals 1 implies a flat prior. We don't know very much about what the probability is going to be. Here's the binomial likelihood. The thing that makes it a likelihood is that it's got an observed argument here, and that's where we pass the data. So these are the actual observed home runs, and then n is the number of plate appearances. Okay, and there's one for every player. So the dimension of this is player, and then we allow PyMC to do its work, to do its magic, to calculate posterior or sample from the posterior distribution. Okay. All right, and this is what ends up happening when you fit this model. So every line here, every colored line is one of hundreds of players. And most of them are kind of bundled up towards 0, somewhere between 0 and 10%, which seems like reasonable home run rates. But you can see that it extends all the way out to 1. So you've got a small number of players that, hit home runs at a 40, 60, 80% clip, which doesn't look great, right? We don't expect that to happen. Hitting home runs is hard. And so if we look at some estimates from this, so in this is just an arbitrary sample of players. The red dot is the observed home run rate, and then the blue line is our estimate from our model. And you can see that for some players, it's got a really tight confidence bound. So the line represents the uncertainty. The thin line is a 94% interval, and the thick line is a interquartile range. And what's happening here is that a lot of these players have had lots and lots of at-bats. Alec Boehm, Darren Ruff, Elias Diaz. But others, Nate Mondow, Ronnie Dawson, have maybe had one at-bat, two at-bats. And so it's leaning heavily on the prior. It's shrinking back to the prior, which, as you remember, was a flat beta distribution. Everything's equally probable between 0 and 1. So the sampling worked for all the players, but you can see that some are far more uncertain than others, and the uncertainty is related to the number of plate appearances, as you'd expect. And if you can identify batters with high home run rates, estimated high home run rates, by plotting the ordered mean as well as the interval. And you can see everybody with a really high estimate also has huge uncertainty. They're all highly uncertain. Or viewed another way, we can plot the interval width, just uncertainty versus plate appearances, and all the uncertainty are for players with less than, a couple dozen plate appearances. The problem with this is that it's not a very useful or informative model unless you have a ton of data. This is what's known as a unpooled model, where every player gets a separate estimate for their underlying rate of home run hitting, or their innate ability for hitting home runs. What we're going to do instead is jump to something else that is a little bit more sophisticated, that takes advantage of the fact that we know something about how baseball players behave. We actually have a population of players that hit home runs, and we can model the population of corresponding home run rates. So we build what's called a hierarchical model or a partial pooling model. And so now everybody gets their own estimate for home run rates, but those home run rates are drawn from a distribution with particular parameters. So they're kind of constrained to be within a particular range. And this should get rid of some of the ones at the high end, or all the ones at the high end, because those tend not to be observed in the real world. So here's our partial pooling model. What we're going to say now is that our probability of a home run is going to be normally distributed on the logit scale. So we're going to work on the real line and then convert it into a probability using the logit transformation. And it's going to have hyperparameters, a mean and a standard deviation. It's easier to think about things in terms of mean and standard deviation. So it's going to have a particular mean, particular standard deviation. If the standard deviation is small, the players will be very similar to one another. If it's wide, it allows them to be very different. And so that's what this model looks like here. This is exactly this model specified in Python. Notice essentially the same number of lines. So you can see the random effect, the partial pooling bit at the top, the mu and the sigma. We combine them for a prediction of P, and the binomial distribution is essentially the same. And this is what that model looks like. So now we have sort of hierarchical levels here. Home runs is a function of home run probability, and home run probability in turn is a function of the distribution of the population. And if we compare those, on the left-hand side here are the unpooled estimates with lots of extreme values. On the right are the partial pooled estimates. And now you can see everybody's now been pulled back into a realistic range. To give some context, you consider somebody like Barry Bonds, who cheated at baseball but hit a lot of home runs. His home run rate was about 15%, and that's like all-time high, right? And so you really shouldn't get many above that. And so as you can see here, everything has been shrunk back to well below kind of 10%. There's a few point estimates that get close to 10%, but we're fairly confident, even with very little data, that it's not going to be a historically great home run hitter without any evidence otherwise. And then the corresponding estimates now are also a lot more reasonable, right? Who were they from before? Ronnie Dawson, Nate Mondow. They still have the widest credible interval, probability interval, but it's not all the way out to 80% anymore. So we have much more reasonable estimates. And we can expand beyond this, right? We know other things about baseball players. We can say that, we can incorporate the position of the player, right? Catchers and shortstops may not hit as well as corner outfielders and corner infielders. The team, you play in a hitter-friendly ballpark like Houston or like Colorado, may influence the kind of home runs that you hit. I won't get into the depths of this here. I'm going to kind of try to jump to Gaussian processes here. And that where that becomes useful is where we want to add maybe continuous variables as predictors. Maybe these things change over time. I provided you with kind of a static snapshot of how home run hitting is working in a particular season. But what about age? Things vary with age, right? You can imagine ability varies with age. Maybe you get better as a young player, and then maybe you plateau for a little while in your peak, and then you decline again as you get older. How do you specify those? It's not as simple as simply adding, a regression coefficient, because these could be nonlinear and complex in potentially unknown ways. So Gaussian processes are a way of adding flexible, potentially nonlinear effects to any model, including a hierarchical model like we've already started to build. Gaussian processes is essentially building a little model with with a bunch of Gaussian distributions. And this may seem odd. How can you build a super flexible nonlinear model with a Gaussian distribution when Gaussian distributions, as you see here, are pretty plain Jane, right? They're narrow. They don't have a lot of variation around the mean. They're symmetric. What we end up doing actually is using a whole bunch of normal distributions to model complex nonlinear functions. And in fact, we're going to use an infinite number of Gaussian distributions. So let's dig into why we might use a Gaussian rather than something else like a student T or a binomial distribution. Gaussian distributions look like this. So we're going to work with multivariate Gaussians. So they have means and a variance covariance matrix. So this is showing a bivariate normal that are correlated with one another. Y1 and Y2 are correlated with one another. There are two important properties of Gaussians that make them really, really useful for this type of modeling. One is that they marginalize really easily. What is marginalization? It means that if you've got a whole bunch of Gaussians in a multivariate Gaussian, and you're only interested in one of them or a subset of them, you can do that without it having to do any manual integration. Normally, you'd have to integrate, right? If you just want P of X, you'd have to integrate out Y. But in a Gaussian, all you have to do to get the marginal for X is pull out mu X and pull out sigma X. No math. Easy peasy. Okay? So it makes it easy. We're going to be dealing with infinitely dimensional Gaussians, and you can't deal with infinity. You got to be able to pull out the ones that you're interested in, and the marginalization property allows you to do that. The other thing that's really easy is conditioning. You may want to condition the value of one variable in your multivariate normal on the observed values of others. So what's the probability of X given Y? It's not quite as easy as the marginalization, but you can see here it is at least in closed form. You can just plug in values here, and other than the nasty matrix inversion, it's all pretty easy. No integration is required. So you can marginalize, you can condition. So given all that, what the heck is a Gaussian process? Well, if you consider a Gaussian distribution to be a vector of Gaussian random variables that are associated with each other via a variance covariance matrix, sigma, a Gaussian process is a distribution of functions that is parameterized by a mean function and a covariance function. Okay, so it's generalizing a normal distribution to be infinitely large. So from the standpoint of a computer scientist, how would you deal with a vector of infinite size? You can't store it in memory, right? It's not possible. What you can do instead is write a function. And a function would return any value that you want from that potentially infinite vector, but you don't have to store them all at once. You don't have to store them in memory. You just have to provide arguments and it'll return you a value. This is the same idea here. So we have a mean function and a covariance function. you supply it with values for x, and it'll yield a function back for you. So a Gaussian process, by definition, is an infinite collection of random variables, any finite subset of which have a Gaussian distribution. So think back to the marginalization. I take a subset of my infinite normals, and I get a multivariate normal that's finite, and that's something I can work with. Okay, so it kind of looks like that. The advantage of Gaussian processes for building nonlinear models is that it works with the function directly. It's a model of directly a model of the function. If you're building a regression model, a regular regression model, even a polynomial one that's nonlinear, you're modeling it indirectly. You're modeling a bunch of parameters, and then you add the parameters together to yield a line. Here, every time we sample from a Gaussian process, we get a wiggly line. Let's look at the components here. The really important component of a Gaussian process is the covariance function. And the covariance function is, as you might have already inferred, a function that yields covariance matrices. So you pass it some x values, and it spits out a variance covariance matrix that you can use in a multivariate normal. This is the powerhouse of the Gaussian process. This is what makes it go. This is what makes it work. This is what characterizes how it behaves. And there are a whole bunch of different potential covariance functions. Covariance functions you can think of as sort of a distance measure. So for any stationary covariance function, things tend to be similar when they're closer to one another, and less similar when they're further apart. So as you can see here, when x and x prime get farther and farther away, this gets closer to 0. When they're exactly in the same spot, the numerator goes to 0 and it becomes 1, and they're exactly the same. So this relates to how similar nearby points are in a line, in a function. Okay, and it has a couple parameters. So this one just has one parameter, a length scale. And as the length scale gets small, the line gets kind of wigglier. But we have different covariance functions. That's an exponential quadratic. This is a matern, and it's a little rougher. It's got kind of a roughness parameter associated with it if you have something that kind of jumps around a little bit more than that one. So you see how smooth that one is. We can even have non-stationary covariance functions like cosine. Let's say you're modeling something that's seasonal. You could use a cosine or some other sinusoidal covariance function. And the cool thing about them is that you can combine them together. You can take two different exponential covariance functions, add them together, you get another covariance function. So let's say in terms of a temporal model, you could have something that's operating on a small time scale added to something that operates on a long time scale, and you can model them together. You can see how this looks very heterogeneous. So you can add them together. You can even multiply them to get weirder things. The mean function is far less interesting. I'm going to mention it here and not again. It really just describes how we expect the function to behave in the absence of data. So it really is a prior. It gets overrun with almost any data. And so we think of this as kind of a prior guess at what's going on. So a lot of the times you'll just see a zero mean function. It just returns 0 for every value, or you might make it constant at some meaningful constant value. But most of the time, the mean function goes away once you add data. So we won't really work with those in any great detail. So here's an example: a mean function of 0, a exponential covariance function. This one has an additional parameter called theta 1 here, which is the amplitude, essentially, that describes kind of how things vary along the y-axis. And it's very simple. It's very, very easy to implement. And the result of that, you get, this is what kind of samples from a prior with that mean function and that covariance function look like. Okay, so we have a distribution over function. Realizations are functions, right? And without any other information, this is just defining a range of potential values that a function could take. And then the data will help shape what the actual function will look like. These are just draws from the prior. A cool thing is that if you get a Gaussian process as your prior and you pass it Gaussian data, normally distributed data, a thing like a phenomenon called conjugacy kicks in, and there's actually a closed form Gaussian process out the other side. Makes it really easy to work with and calculate. A lot of the times, though, we don't have Gaussian data. We've got binomial data, like in our case. So we can't work with this marginal Gaussian process. What we're actually going to work with here is what we call a latent Gaussian process. Whether we have something like binomial data, we may have a Gaussian process prior, and then we have to kind of transform the Gaussian process, in this case, to be on the 0-1 scale so we can use them to model probabilities. So we're going to work with latent Gaussian processes here. So here's an example, right? Let's say I want to add age to my model, right? I want to see how home run rate varies with age. So now the priors that I worry about are the hyperparameters of the covariance matrix. So that length scale and amplitude that I talked about before, there they are. So I'm going to put priors on those. And I've picked two distributions that people in the business typically use for those sorts of things. Don't worry about them now. The whole business of prior choice is kind of outside the scope of this talk, but it's an important one. But those are reasonable choices. And then having done that, we build a covariance function. So I multiply the amplitude by the quadratic exponential function, covariance function with the length scale. And I create a GP, a latent GP. And then I evaluate the prior over all of the ages potentially that we see in our population. And now we have an age effect. So F here is an age effect. And then use that to calculate the probability of home run, and boom. So it sounds great, but the problem is I've got hundreds of players here. And one of the constraints of particularly latent Gaussian processes is that they're very computationally intensive. And the reason that they're computationally intensive has to do with what we see in the posterior distribution of the covariance function. That's what this is here. So K star is the posterior covariance function. And what you see right in the middle of that is the inverse of a function of a covariance matrix of the data. So let's say we have, I don't know, 1,000 players. We're trying to invert a 1,000 by 1,000 matrix. And you can go off and try to invert a 1,000 by 1,000 matrix in SciPy after you're done this, see how long it takes. And you got to do this at every iteration of our model. So this is very computationally intensive. And so what we have are some really clever approximations that we're going to focus on here. And Bill is going to dig into quite deeply in his case study when I'm done here. And the best approximation here is something called a Hilbert space Gaussian process, or an HSGP. This is a parametric approximation to a non-parametric. So Gaussian processes are all often referred to as non-parametric Bayesian models, which is kind of weird because they actually have an infinite number of parameters. But really it means that we have the number of parameters that vary with the size of the data. And what the HSGP is going to do is it's going to have a parametric or a finite approximation to that. And it'll take it from, so the thing about this, I forgot to mention it, though it was written there, it's cubic in compute time, which is really, really slow, and quadratic in storage, which is sometimes what gets you first. For HSGP, it reduces that cubic compute time to mn plus m, where m is much, much smaller than n. It's the lower rank approximation that we're worried. So we're going from thousands here to, I don't know, a dozen or something like that. And so what we're essentially going to do here is we're going to replace the exact GP with what is essentially an analog of a linear model. We're going to have a bunch of basis functions to replace the Gaussian process. That's phi here. And the basis functions only depend on the inputs, the data. And then the coefficients only depend on the hyperparameters, namely the length scale here. And so this is, we're just multiplying data with coefficients, which is just a linear model, right? And so this is fast. And so what we worry about here instead are the HSGP hyperparameters. How many basis vectors do we pick? What's happening under the hood here is a spectral decomposition of the variance or the covariance function. And we can approximate that with basis vectors, kind of like you do with a spline. And the more you have, the more faithful the approximation is. But of course, the more computation that you have to do. The other thing you have to worry about is the boundary of the space. This approximation only works over a defined range of values of inputs. And so you have to be specific about where you need to be using this GP, and you'll ignore any areas outside of that space. The extension factor is kind of related to both of these things. It's sort of the number of, if you take the width of your data, how many multiples of that width that you're interested in extrapolating, essentially. So these are the hyperparameters of HSGP that we're interested in dealing with. And we choose these based on a bunch of criterion. How accurate do we need our approximation to be? How computationally efficient, or how much computational power do we have or are we willing to use? And then where do we need to use it? We don't need to worry about approximating things way outside the range of our data. To give you kind of a feel of how this works, at least in terms of the range of the data, is if you pick C equals 1, like only being the range of the observed data, what'll happen is that the basis functions will all bunch together at the boundaries of the data. And this could be problematic because it's a complete artifact of the methodology and doesn't really reflect what's going on in the data. If you expand it to say 20% beyond the range of the data, you see it becomes a little bit looser and more flexible, 4 times the range of the data. Now the basis functions can kind of do whatever it wants. That's kind of the idea. But again, it comes at a computational cost. Okay. What does this look like in PyMC? I want to add an age effect to my model, my home run rate model. We still need our amplitude and length scale from before. That's no problem. We still have the same covariance function as before. So this is exactly the same as before. Here's where the HSGP kicks in. I specify a value for M. So here I'm saying I want 100 basis functions to approximate it. That's quite a few. I probably don't need that many, but I can do it, so I will. And then I'm going to take 3 times the width of my data. So that looks like plenty. And then here's the covariance function. Don't worry about drop first. I'm not going to explain that. It's not super important. And then that's my prior. Just like before, I evaluated at all of the ages. The nice thing about this problem is that there's only a discrete subset of ages I need, from like 18 to like 42. I don't need fractional ages here necessarily, at least for not for this problem. And then the likelihood is this. Then now I've got my mu. So everything else here is from my hierarchical model from before. So epsilon is my individual random effect. Theta is my team effect that I showed you at the graph. Mu is my position effect. And now I'm adding an age effect. So now I have a pretty sophisticated model that's based on individual variation, Park effects related to the team, position effects, and now an age effect. And if you run this using MCMC, it actually runs really fast. This one only took a couple minutes instead of, years it would have taken if I was going to try to use an exact GP. Okay, and so you get something like this. So this is what the posterior GP looks like. And, I haven't refined this model at all. This probably isn't the greatest age curve. I'm also only using a static year. You ideally want several years so that you can model, so that individuals are allowed to change over time as well. But you're seeing a gentle decline in home run rate with player age. There's a bunch of other factors that I haven't taken into account, like selection bias and so on. But this is just meant to give you an idea how to implement this stuff. So just a couple caveats with HSGPs. They can only be used with covariance functions that have spectral decompositions And typically those are stationary ones, although you can do it for a couple of the sinusoidal functions. It doesn't scale well with input dimension. That is, if you do some complex spatiotemporal model, you can probably get away with like 2 or 3 dimensions, so x, y, and z. So latitude, longitude, and time. Beyond that, it tends to break down, and then it can struggle with processes that vary quite rapidly. Okay, I hope that wasn't too much too fast, but it's time for me to hand it over to Bill, and he's going to take all of this goodness and build something fun with it. So let me relinquish my screen share and let Bill take over.
All
Ready,
right.
Bill?
Yeah, I think so. Thanks, Chris. That I'll try and pick up where you left off here. And Chris has got to bounce to go teach a class. So yeah, tight schedule. Let me do the share screen thing. Um, okay, um, so what I'm gonna do is kind of, Chris gave a nice introduction to what Bayesian modeling is, what hierarchical modeling is, what GPs are, and then, kind of how to start dealing with some of the challenges that come with actually using GP models in practice, which is, the one he touched on was computation, right? Where he had to, you have this HSGP approximation so that you can actually fit these models in practice. So what I'm going to do then is try and kind of tie that together in a notebook and kick the tires on it a little bit. And I'm going to kind of explain how GPs are, instead of kind of the more common definitions that people have seen before, and that Chris showed, kind of show how they can kind of come naturally from just a hierarchical model. He kind of hinted at that. And that can be kind of an easier way to wrap your head around them at first, especially if you're in the context of a PPL or probabilistic programming language like PyMC or Stan or Pyro or something like that. So, and I'm also going to spend a lot of time, and I might have to rush through some stuff, but hopefully this can be a useful resource to come back to for people, on how to sort of how to debug problems that you'll have when fitting GPs. I know my experience, at least with these, learning them was the theory is really cool. In practice, it can get a lot harder. It's sort of, the first time I try and fit one, it doesn't sample right the first time, like ever. So there's always some debugging that sort of has to happen. So, you know, um, let's see. You might think about using a GP when, like Chris said, you need to regress out a more functional effect. Another one is like forecasting. So unlike splines or polynomials, GPs can be used to make pretty reasonable and interpretable extrapolations outside of the domain of the observed data. Um, and something that you can understand why it's doing what it's doing. And then this sort of last one is sort of where we're going to focus here, which is like when you have a hierarchical component in your model, but the groups in that hierarchy aren't entirely exchangeable. And maybe the thing that's linking them isn't just that there are different categories, but maybe there's some continuous thing like age. And so that's what we're gonna build on here. So, you know, so kind of going back to Chris's example too. So we're modeling the batting average of baseball players using a data set that looks kind of like this one. Here's the first few rows of it, right? So, you know, pretty straightforward. CJ Abrams plays for Washington. He's 22. He had 559 at bats, 138 hits with a batting average of 246 and a slugging average of 415. And in this, we're going to start by estimating the batting average of each player. And this is another take on the, binomial model, the binomial likelihood model that Chris presented, and it's pretty similar to this example here, on baseball also. But we'll simplify things for a little bit for the sake of just explaining this stuff. So here we're starting with, um, just sort of your standard hierarchical model, and we're not bringing in GPs quite yet. So in this model, this sort of hierarchical structure makes sense because you can treat each player as exchangeable. Each player has their own batting average estimated, and it doesn't matter if we sort of shuffle the order of the batters, or we remove players or add players. Um, the sort of how the model's structured kind of remains the same. So players that had, not many at bats, like Jordan Adams here for LA, he had 39 at bats, or and so, they're gonna have their estimate pulled towards the average of all players. Um, the assumption that underlies this is that, okay, maybe we haven't seen, maybe Jordan underperformed or had an injury, right? You can see his batting average is kind of on the low end, 128. Um, but he had few at bats. So, he's a major league baseball player. He plays for the Dodgers. He's probably by the end of the season, or if he has more at bats, his average might get pulled towards the average of the rest of the players. Um, so, you know, with more opportunities, right, his performance is likely to regress to the mean. Um, so here's the model, and then let's just fit it and see where things stand. So by the way, here's I'll kind of since I'm talking over the code a little bit, you can use pandas.factorize to get the indices of the players and then the labels of the players, and then this chords object in PyMC right here. This player corresponds to this dimension. And now instead of having to try and remember all the indices of the player effects, there are going to be you can index them by their name. That's what this is, which is really handy for working with the results of these models. So yeah, that's here again. So and then we're also sampling it using the NutPy sampler, which is pretty brand new, and it's written in Rust. And Adrian Seybold did this, and it's very fast, and you can either use the Numba backend or the JAX backend with it. But it works really, really nicely. Um, and so yeah, here's our results. So you can see how, like I was saying, the coordinate on the player's batting average here, now it gets recorded with their name instead of just like index one, index two, index three. So yeah, the you can see that the results look pretty nice. No divergences, which mean and R hats are all fairly low. Sigma player is a little borderline, but we're gonna skim past this example to move on to GP stuff. But yeah, so that's sort of doing the right thing. Yeah, you can see the convergence issues of Sigma player here. So, and here's your estimate then for Jordan Adams, right? And you can see that his his batting average posterior gets pulled up quite a bit, somewhere between zero point 0.2 and 0.27. And this little gray line, that was his observed average. So, you can see that the model's not entirely trusting that just because he had so few at bats, that's his sort of real true batting average. Um, and so, the key thing here is that since players are exchangeable, since we're treating them as exchangeable, the partial pooling that's affecting Jordan Adams' batting average is coming equally from every other player. So, what if the players aren't exchangeable? Often, the more we learn about our data, the less likely that the exchangeability assumption is going to hold. So, for example, there's the age factor, right? What if we want our model to sort of have this nice partial pooling behavior, but we want to partially pool. What if we think that like information on batting averages is more likely to partially pool locally, right? So like over players that have similar ages. So, you know, young players are more similar than older players, we might assume. We're not going to assume that, maybe you could in some contexts that, younger's less similar to middle and then more similar to older and have some sort of periodic effect there. That's possible, but for the time being, it's just safe to assume that, younger players are more similar to younger players, older players are more similar to older players, and we don't know exactly, that's just an assumption we're building in, and we don't want to build in how strong that assumption is, right? So we could have an age effect that is not a GP, that's just like a standard hierarchical model, where we only then partially pool players that have the same age. So we would then only be comparing, Jordan Adams to all players who are 23. But that doesn't really make sense. We want to include players who are 24, 25, 26, and maybe figure out how that relationship sort of decays as ages as ages between players get more further apart. So, you know, we can use a GP to accomplish this. That's kind of what a GP is, really. And to kind of see how we get there as kind of a stepping stone, let's rewrite the same model we had, but use a multivariate normal with a diagonal covariance instead of a vector of IID normals. And these things are exactly equivalent. So that's written here. You'll notice I'm using the Cholesky factor. Like that's kind of a matrix square root, because calculating it every time is why GPs are slow. And since it's a diagonal matrix, you can just calculate that without doing a full matrix like Cholesky decomposition. So yeah, you'll see that you'll fit this and you'll get the same results. So it's the exact same thing, and you'll notice that Jordan's Adams result is exactly the same as it was before, give or take, little bits of difference from random seed. So there's no covariances being induced by our prior in this case, right? If there were, so, our prior is the identity matrix, right? So that's values on the diagonal, nothing on the off diagonal. And if there were covariances between players based on age, then we'd have in our prior, then we would have off diagonal elements that weren't zero. And so, well, how do we do that, right? How would we what makes sense as a way to build a prior that incorporates the player's age then? So instead we can use this thing called a covariance function or a kernel. Um, and it's a function that takes two different ages. So you're comparing two different players, and it returns a larger value. This is their covariance if the ages are similar, and a smaller value if they're different. So that function's not too hard to come up with. Here's an example of one function that does that. This one has a name. It's called the exponentiated quadratic kernel or covariance function. And I'm kind of using it here because it has a particularly simple form, right? So X is age, and if the two players are both 25, then this is 0, and e to the 0 is 1, right? And then you get, so then the covariance reduces to just eta, the scaling, which sort of tells you how important age is generally. And then if the ages are different, like if this is, if one player is 10 and the other player is 200 years old, then this is going to be, a big number, and this whole thing is going to go to 0, right? Um, but you'll notice that there's two unknown parameters that are kind of mediating the strength of that effect. So they're called eta, which is the scale, and the length scale L. So eta plays the exact same role as sigma does in a normal hierarchical model, right? If we go back to our identity matrix example and you just had eta times the identity matrix, then you can see that it's doing the exact same thing. That's why it's squared here too, by the way, is to keep that interpretation accurate. So, so you know, sorry, I lost my place. It scales the overall size of the effect, which is the total amount. So that's like the total amount of partial pooling, right? Then the parameter L, the length scale, is brand new now. So this is what kind of is taking our hierarchical model and turning it into a GP. So it's called the length scale. And it determines what we mean by close when we say one age is close to another. Um, so, in our baseball example, right, age is measured in years. So close might be, the length scale equals 1 year, right? Um, and these are parameters that we don't know, and we want to learn them from the data, right? So just to be clear, if if the length scale is equal to 10, that means that 10 is more the scale that we think ages are similar. So it's not like a hard cutoff. Like if the ages are 10, then that's similar, and then 11, they're not similar, right? It's kind of this is a very Gaussian looking function. It's kind of where the Gaussian curve kind of, you know, changes and levels off. It's kind of maybe how you think about it. So it's like a soft cutoff. Um, you know, and you should note here too that we should be able to set pretty informative priors on the length scale, right? So for our age example, clearly the length scale of 0.1 is way too small. Players' batting averages is not going to change significantly if they get a month older, right? They get injured or something, but like not just from aging at that time scale or an hour older, right? And then also a really large length scale like 100 is also extremely unlikely because that's more obviously in the scale of like a person's lifespan or past it, and not just the sort of the span of their professional baseball skills. And so, since this length scale is so interpretable, we'll often be able to set fairly informative priors. And then, as I'll kind of explain next, like setting informative priors keeps you away from a lot of problems that you're going to have sampling these things. So, here's an example of what this covariance function looks like at a particular length scale. So here's an X that represents ages. So we have it ranging from 20 to 30, and a length scale equal to 1.5, which, that's a value that's in that scale, right? And so you can see that you can interpret this matrix as reading, okay, so the 0th element is 20-year-olds to 20-year-olds, right? There's no difference in their age, so that's equal to 1 because we have eta equal to 1. But from a 20-year-old to a 21-year-old, that's this cell here. I don't know if people can see my mouse. I hope so. But I'm pointing at, actually probably not. I'm pointing at um, the first row and the second column. That's going to be age 20 compared with age 21. And then age 20 compared with age 22. Age 22 is going to be the third column. And you can see that if you just work across a row, because this matrix is comparing every age to every other age, then you can see how a length scale of 1.5 kind of decays the dependence on age as ages get further apart. So, when someone's 20 and someone else is 30, there's no relationship between their data, right? We're not going to be, if we use this in our age example, we're not going to be partially pooling information for 20-year-old players that's coming from 30-year-old players. We've isolated them from each other. Um, so yeah, exactly. And then the takeaway here too is that just a high value in this matrix means that if a pair of x's are similar, that means the values of the GP, their effect, are going to be similar there too. So similar ages imply similar batting averages. That's the assumption that underlies this. While the parameter eta kind of is responsible for telling us how true that assumption is or how strong it turns out in practice when we fit this to data. So, I'll go back to what is a GP, right? So Chris gave that introduction already too, and I'm just going to kind of come at it from this perspective. There's a lot of ways to view these things, because to view GPs, because also a lot of models are special cases of GPs, like autoregressive models or even linear regressions. You can write a kernel function that represents that. So so here's the GP, and it's like a multivariate normal, except that the covariance isn't a matrix, it's a function. That's the difference between those two things. So that means that the overall size or dimension of the multivariate normal is subject to what we decide to plug into that covariance function. How many different points we put in, that determines the size and the dimension of the multivariate normal. So yeah, it's a multivariate normal, but it's a multivariate normal that can sort of shift its dimensionality. And for example, if we have 3 players with 3 different ages, 24, 25, 26, we plug those in, we get a 3-dimensional multivariate normal and a 3 by 3 covariance matrix. And if we plug in 10 players, it'll be 10-dimensional. And if we plug in 100 players, it's 100-dimensional, and so on from there, right? And you can see then that's why GPs are slow. So, but at a basic level, that's really all there is to it. If you tried to learn about GPs before, you'll know that things get more complicated. And just to kind of give a bit of a roadmap, this complication comes in 2 directions, right? One of them is the form of the covariance function. You can represent a lot of really interesting structures using this. So, you know, much more is possible past this sort of simple, um, similar ages, similar batting averages kind of picture. Um, random walks, complex periodic behavior, even covariance that kind of like do the same thing that neural networks do. And then you can add and multiply covariance matrices functions as well. And so you can come up with all kinds of combinations. But the main one is computation, because as you saw, if you implement them naively, GPs are very slow. So there's a lot of different approximations and computational tricks to improve that scaling, and a lot of research on GP stuff is focused there. But at the end of the day, even though all these things are sort of named like different types of GPs, like an HSGP versus a GP, it's still a GP. It's just an approximation of a GP. So this sort of understanding of what you're modeling, that simple one, still applies, even if you're using some pretty tricky approximation. You can still think of it using kind of a simpler mental model. So, before we get back into baseball modeling, let's take another step back, because when you're fitting these things in, and I kind of, for people following along, I hope this doesn't get too boring, but maybe when you're fitting GPs later, you can get some errors and come back to this and maybe get a little bit of help. So, because some of these things can cause some frustrations, because, unlike other priors that you may have used in Bayesian models, GPs are super sensitive to the priors that you're going to put on eta and the length scale, and particularly the length scale. And this next section, I'll explain why. So we can sort of get that out of the way and then just fit GPs without too much frustration. So, so let's look at the limiting cases, right? So when the length scale goes to 0, what happens to this covariance function? So when the length scale goes to 0, we actually talked about this case before. You can kind of factor this term and put the length scale under the x's like this, and I think it looks a little more natural because you can see how the length scale is dividing the x's. But you get the identity matrix again. This is exactly the same as when we were using a multivariate normal in the batting average example. So, here's it proven with code, right? I have this 10 ages and I'm plugging in a very small length scale, and lo and behold, you get the identity matrix back. So there's 2 important points here. The reason it's important for modeling is because when the length scale is small, your GP has reduced itself to a normal hierarchical model. And it's important to sort of spot when that happens, because for one, it's going to be a lot faster if that is what's going on and there's no kind of age relation and they're all independent from each other, that's what this is saying, then you should probably code it as like a normal hierarchical model and not a GP because that will sample way faster. And then, if the length scale, the other important point here is that if the length scale ends up being smaller than the resolution of your data, you're not going to be able to detect those differences anyway, right? You can't measure a length scale of 0.1 versus 0.2 when all the baseball players' ages are like integer values. Those are just going to look the same. They're just going to look like the identity matrix. So if you've specified in your prior that there's a lot of mass at resolutions of the length scale, at length scales smaller than the resolution of your data, then you're going to have some issues. So here's this illustrated. So the black is draws from a random normal, and then these other colored curves are what happens if we smooth them out using longer length scale GPs. So, you can see kind of why maybe that name kernel comes in if you've seen like kernel smoothing. It's kind of related. Um, but you can see though that like when the length scales are larger, you can visually see the differences in the curve. And then when the length scales get really small, smaller than the age, which are integers, so like 0.5 and z, you can hardly tell them apart. And that trend keeps going. So if you're working on a problem and you encounter this, what's the fix? So the fix is you need your length scale prior to block small length scales, especially if they're below the resolution of the data. If you can go higher than that, great. That'll help you even more. But you at least need to make sure that your length scale isn't sampling, you're not putting priors like at super small length scales that are like smaller than the ages of the players. So that's one thing to watch out for. Like if your prior mass is all between 0 and 1 and you're measuring ages, that's not going to work well. So um here's some examples of informative priors that do this. So there's an inverse gamma. I put the inverse of an exponential in there too. There's a log normal, and then this penalized complexity prior, which is these are all useful. And I'm not going to talk about what that is exactly. But I linked to some, descriptions of it in the notebook. Yeah, that's right here. And the inverse gamma prior recommendation comes from this post by Michael Betancourt. That's great. So you can kind of see how these all behave with different parameter values. But the main thing is it's a little hard to see with the PC prior how I said it, but at small values, it really cuts this off. It doesn't sort of, give a lot of prior mass to small values. So the next one is case 2, when the length scale goes large. And when that happens, you just get, so I'm going to speed up a little bit for time, but you just get an eta, right? You just get this covariance matrix that's all constant, which is weird, right? I think it's a little strange. It might look strange to you, but it's actually possible to draw samples from this and treat it like it's a GP. And what you get are flat lines. Each sample is a flat line, which is of varying height, which is exactly what an intercept term in your model is, right? That's just a level shift that applies to everything. The reason that this is happening is because if all your covariances are the same, then every point is related to, it's like every age is equally related to every other age. And that can only give you a flat line when you're drawing samples from that. So, when your length scale starts getting really large, now you have identifiability issues between the intercept term in your model and the GP. So, the main fix here, and this is showing that again with that same plot of like, the random samples and then increasing the length scale. And you can see that as you smooth and smooth and smooth, that line just gets flatter and flatter. Which makes sense. That's what smoothing does. So, the fix here is to mostly be aware that this is possible. You can consider removing the intercept from your model or removing the GP from your model. If it's trying to be flat, then it's not really measuring an effect, right? So that's sort of the main takeaway here. Using informative priors to help with identifiability issues. I'll skip Well, yeah, we'll see on time. Maybe I'll return to this because this is helpful, but um, I'll start here. So I'll keep going here. I mean, so another thing to keep in mind for GPs is to think about what n is. So how much data do you have, right? Um, if you're trying to learn the length scale on players' ages and you have 1,000 players, but they're all age 22 and 23, that's actually not that much data on age, right? That's only n equals 2, really. So even you could have a lot of data, but not a lot of data that helps you out with your GP. Um, and so that's kind of what a large length scale is, right? Um, if your data has a large length scale, it's changing slowly. It's kind of like saying I'm only observing a small window of possibilities here. And that means that like you don't have much information to actually inform your estimates of the length scale. So, your length scale posterior is going to end up being pretty wide and using that prior to like not make it too wide is going to help you out. So let's go back to baseball. Maybe I'll check the messages just to see if I am like missing any questions. Sorry, just skimming. Um, yeah, no, I think this will be helpful if, especially if you fit some GPs and hit a wall. I kind of wanted to include stuff on that because it's hard to find information on that. So, at least for me, it was. But yeah, so back to baseball. This one we're gonna do the slugging percentage, and it's a bit more interesting because unlike at bats, it at bats don't really depend that much on age, but this SLG statistic really does. Because it measures kind of like a strength or like kind of how hard people hit the ball. So it's the total number of bases obtained per at bat. So proportionally extra weight is giving to home runs. Those are worth 4. Triples are worth 3. Doubles are worth 2. So to model this, I'm going to use a count likelihood over the total number of of at bats, right? So that's either going to be a Poisson or a negative binomial most often. And you know, and we'll, include the at bats as an offset term so we get an estimate of the slugging percentage. So here's a look at some data. And now we're looking at multiple years, 10 years of data. And so it's a lot of data on all the players. And these are, some 3 of the like superstars I put up here just to sort of see what their slugging percentages were by year. They're all pretty high. 0.5, zero 0.6. So let's write down the outline of the model here before I kind of get into the code. So this is kind of all of it together. So there's obviously a player effect. That's what we really want to measure. So it's going to be the most important effect for measuring SL, like the slugging percentage, obviously, because that's the player's skill level. Um, I'm going to use a zero sum normal prior here because we aren't going to be interested in extrapolating to new players, right? There were a finite number of players in 2020 and 2021, and we don't need to sort of like, do the hierarchical model thing and to get estimates for new players. So this zero sum constraint makes all their effects, it requires them all to sum to 0. So that cuts out 1 degree of freedom from your model, which can help with sampling a lot. And then the same thing with park. So different baseball fields, like Chris said, have different sizes and shapes. And so, what'll happen is that if a player plays for Colorado, where you've got altitude and maybe the park's a little smaller, I'm not sure, then they're more likely to have a higher slugging percentage just because of the fact that they play half their games in that one place. And then we also include a season effect. So apparently, yeah, the balls used every year aren't all exactly the same, of course, right? They're not all made exactly the same. And so there can be an effect from juiced ball years where the ball goes a little bit further off the same bat swing. And it's the same way where the ball's a little deadened. We treat the season as a fixed effect, so it's not hierarchical because we don't want to partially pool the effects by season. We don't want to say like, oh, if the average of 2021 was high, then that should bring up 2020. We want them all just independent, and we have enough data to do that, right? It's all the players for every year. So again, we're going to get this model working first before you include the GP. That's kind of always a good rule of thumb, is to add your GPs to a model that is working very well before. um, so you can see there's the fixed effect for season, um, then position. No, it's just player added twice. Oh, it's a mistake. I'll fix that. Was going to add position and then didn't. And then, yeah, then here's your linear predictor. So this is what, it's a log link. So it's an exponential log, you know, inverse link. And I'm using the penalized complexity prior for the negative binomial to handle some over dispersion. And I'm not going to talk too much about that, but as you can see, it's not too hard to implement in PyMC. And I just have this stashed somewhere and I copy and paste it when I need it. But it would probably be nice to have this in the library somewhere for people to use. These are very common in INLA for default priors there, and they work really well. And yeah, there's one for the length scale as we saw before, and we'll use that. So here's sampling again with NumPy. Took 35 seconds to sample, pretty good. And here's our results. So again, no divergences. Our hats are all one. And sorry, I can't remember if I resampled it after I got halfway through adding position and then yeah, I know I didn't because I didn't rerun it. So I will push that fix. So the results, yeah, no divergences. Our hats are all one. That means the results are trustworthy. So let's look at the slugging estimates from a few famous players. And these all look in line with what we might expect. Right? These are all pretty high and pretty good uncertainty because I think that's not coming from a lack of data. It's because if you look at year by year, right, a player's slugging percentage can change quite a bit. So, Aaron Judge one year had 0.7, which is really high, and 0.34 another year. So smaller number of at bats, but this hierarchical modeling makes sure those are all weighted together nicely. Um, so that's where that uncertainty is coming from. But yeah, let's look at the top 10 and using our inferred slugging percentage, factoring out the effects of season and park, of course. Age is still not accounted for, but that's okay. And just sort of see what we get. And yeah, the interesting one, I think here, so there's the usual suspects right here at the top. Reese Hins is kind of interesting because he has a small number of at bats and a pretty high calculated slugging percentage, and then his effect is still pretty high. So, he has enough at bats that it seems like he's probably pretty good, even though he hasn't, played that much. And then Carlos Rivero too. So we'll look at their data here, and you can see that Reese Hins was Hines, whatever, as he's 23, so he's new, and in this year, and then Carlos played just 1 year in 2024 for a limited amount, so he's probably not in the majors anymore. But yeah, so that much more work would be required to sort of verify this, but maybe he's an interesting player to watch, right? So um now let's incorporate age, right? Last 10 minutes, this is the whole deal. So we've got a working model. It's time, that's sort of what we need to add age in. So what we're going to choose, here's sort of the summary of what we're adding. So an exponent, we're going to start with our same covariance function. We'll find that it doesn't work and we'll change it later and talk a little bit about why that is, because that's a very common rake people step on, is using this covariance function as a default when it's a very bad default, especially in the context of a probabilistic programming language. And then we're going to use a PC prior on the length scale L. We're not going to mess around with bad length scales and seeing what effects they cause. We're going to say there's only a 2.5% chance that the length scale is less than 5 years. That's how we're going to calibrate that prior. Um, you know, and then we're going to use an exponential prior on the scale eta. And we're going to say that we think there's a 1% chance that the scale is larger than 0.2, which is pretty big. Since we're setting these in the log space. And the exponential prior is nice because I like it because it has large tails, and so, the data could surprise you if your prior's not quite right. Um, and we're gonna use the HSGP approximation that Chris introduced, and you can use there's a handy function in PyMC to set M and C when you have one input dimension, and that gives you a suggestion on which values you should start, given the range of x values you're looking at and the range of length scales that you need to accurately represent. And it's always okay to liberally round those numbers up. That's only at the expense of increased compute. So here's the model below. So everything else is the same except for the GP part, which is right here. So you can see our scale prior and you can see our length scale prior. This is again the PC prior for the length scale. It's looks kind of complicated, but yeah, again, I just did it once and copy pasted. So um and then yeah, here's our HSGP. And again, I rounded up M and C. Um and everything else is the same. So let's see what we get. Using the same sampler settings, lots of divergences. So that's not great. Um, so we've got some problems, and this is what usually happens the first time I try and fit a GP. So the first fix is the easiest one. You switch covariance functions to not use the exponentially quadratic and switch to a different one that has kind of it has a more clunky form, and it's not the best to sort of explain how covariance functions work, but in practice it works a lot better. And the reason it does is because it's less smooth than the exponentially quadratic. And you can see this here. So these are all the same sort of random seed, and the exponential quadratic are super smooth, and the returns are a little rougher, especially the 3-2. Um, and these work better in practice because, well, I mean, there's some complicated math reasons, but in a simple way, like things are usually this is sort of a strong prior that you're applying that says the thing I'm measuring is very smooth. And that might not be true. So I think Matern 5.2 is a much better default. It kind of balances those two things. And then the other fix we needed to do was parameterize it using the centered parameterization. The default is non-centered. So again, if you've messed with regular hierarchical models, you'll have centered and non-centered parameterizations, and you choose which one depending on how strongly the data is informing the unknown parameters. So um, in this case, since non-centered wasn't working very well, that tells us that there's probably a pretty strong age effect, and the centered parameterization is going to work a lot better. So those are two simple, easy fixes. And once we implement them, so we have to rerun this, we need a bigger M and a bigger C because that return's a little rougher. Very small changes to the code, just this parameterized centered and, exponentially quadratic to Matern 5.2. Everything else is the same. And now we run it and we get only one divergence and usually zero, but, bad luck. But didn't turn up target accept, didn't increase tuning, didn't do anything at all. So it's sampling really nicely. And all of our R hats are very low. So we can trust this result too. And here's the curve we get for the slugging percentage by age. So this is where the somewhat common for baseball knowledge is that the players tend to peak at age 26. That's kind of where this comes from. So you can see that very plainly here that the peak of this curve is right at 26. And young players start out pretty good, then they peak, and then the decline is a little harder, and much older players are not hitting a lot of home runs or triples or doubles. So yeah, that's the conclusion. That's the whole talk. And sorry, it started at we went from very basic to just what's Bayesian to what's GPs to like some pretty advanced how to fit GP stuff. And what to do when you run into problems and why those problems kind of occur. So I hope this talk's useful for people. And before I kind of conclude, I'll check the messages and see if I missed any questions that I can try in the last 5 minutes. But yeah, hopefully I haven't lost everybody. Let's see. Comparing orange to apples in my questions. This PyMC models allow fine tuning. Oh, sorry. Oh, I see. You asked about XGBoost with output to probabilities. Yeah, yeah. Well, yeah. No, they're both useful things, but these kind of probabilistic programming models, you can really fiddle with the structure, right? And with something like XGBoost in trees, you sort of need to have enough data so that the trees or the neural networks or wherever you're using have enough data to learn that structure. Whereas this stuff can work a lot better, especially in smaller data environments where you can just tell it the structure and it just figures out the parameters. So that can help. So yeah, no, thanks for watching, everybody. I'll just go back and do the little conclusion then. So, the conclusion is that another way to motivate and introduce the concept of a GP is as an extension to a normal hierarchical model that you've maybe seen before. And the other one is that fitting GPs using MCMC can be particularly tricky. And, we quickly ran through why that is. And it's kind of all comes down to identifiability issues and corner cases and what exactly those are doing in your model. And then kind of, if you know what it's doing, then the fix is kind of straightforward. But in general, the sort of overarching pattern is use more informative priors. If you don't think that, 100-year like is a good length scale for age, then don't put a prior that puts a lot of mass there. The GP will have a hard time with it because they're kind of weakly informed. And then, we build a pretty non-trivial model for the slugging percentage, the sort of number of bases obtained per at bat. And, even if we start with a good length scale prior, we still had issues with sampling. And we solved those with two pretty easy, but I think pretty overlooked fixes. So the first one is just using a Matern 5-2. A 3-2 would have worked fine too, instead of the exponentially quadratic, because this one is too smooth. And you'll come across cases where you'll have a bunch of divergences, and maybe it's kind of a combination of the centered versus non-centered and how smooth this is, but usually you're just going to have an easier time using this because it does not have such a strict prior assumption on the smoothness. So yeah, hopefully this can help you build GP models, and then when you do, avoid some frustration. So when you go, oh wow, that's cool, I'm going to try this out, and then you try it out and it completely fails. So maybe this will help you avoid some of that. So yeah, that's it. Thanks for attending. Appreciate it. Oh, Sammy, questions in Q&A. There's 2 minutes. I'll try. I did miss that. I'll try and read those. Are you the real Chris is. Chris worked for the Phillies for a while. I have not worked in baseball. But yeah, so rule changes over year. Having a year random effect to affect that slugging percentage is a good idea. It's not just the ball then. Could be rule changes too. That makes sense. How is Shohei Ohtani an outlier? I don't remember the context. Sorry for the question. Is 700 a good sample size sample? Is adding minor league players a good idea? It depends on what you want to do, what you're trying to measure. So what data you include in the model, right, is up to you. If you're trying to measure the effective age on Major League Baseball players, then no, you don't want to add minor league. But if you're thinking about all baseball players, then sure. And then you might have to sort of separate, have an effect for like, is Major League, is minor league, or something like that, so that, you're, comparing apples to apples there. So, but yeah, thanks for pointing that out in the Q&A tab. So yeah, we'll also push Chris's deck to that GitHub repo. You know how these things are, kind of finish it up at the last minute. So yeah, no, the repo will look a little nicer in the next few minutes with his slides in there. But yeah, I think that's it. Thank you, everybody. Bye.